Okay, so I think, let's see. You guys know me, I'm Selman, or Salman, I don't know, depends on who I'm talking to. We have three ways of saying it, I guess. Okay, so I'm going to be talking about a paper based on Maddie Hoban et al. From 2011, I believe. Yeah, so it's going to be building off of, so let me just give a quick overview. So we've been talking about non-signaling distributions, Bell scenarios, and then the connection to computation. And I think that this paper is going to build off of the previous one that we did, or the previous talk, which was based on Anders and Brown and Robert Rausendorf, where you had measurements at each site and the outcomes of those were binary outcomes, so just 0 or 1. Here, Hoban et al., they talk about doing just more general types of scenarios, and they sort of want to connect Bell's inequalities to computational power. So just as an overview, we had this idea of like no signaling distributions, and these form something like a polytope. Imagine that this is just some sort of weird dimensional space. And what he does is he talks about projecting down to a simplified space. Instead of considering all no signaling distributions, he looks at a space P of what he calls correlators. So basically, you take the outcomes of all the different parties and then you form one statistic, just one function, which is going to be just take all the different parties, sum up their outcomes. This is actually very similar to, this is precisely the parity that I discussed last time in Robert Rausendorf's paper. And he is going to just analyze the structure of what kinds of things can we say about the computational power just by looking at this reduced space of correlators. So we're going to deal with the general case of n parties, where each of them, so we're going to make things very simple, make sure that each party has the same number of measurements C, and each of those measurements has the same number of outcomes D. So these are the number of measurements per party, and then there's D outcomes per measurement. Also, note that we're going to consider the case where C and D are prime. So Hoban et al., they have a couple of comments about the case. It's not that you can't do it, it just makes life more complicated if these particular numbers are not prime, because we're going to be doing stuff like summing modulo C and modulo D. It's nicer if things are prime. Okay, so just continuing on. So we'd like to think of, maybe I can have a little diagram up here. You have different parties. Say that this is party number 1, or actually, maybe I'll draw the picture here, and then I will go forward from there. Okay, so just imagine that we have something like this. I have party number 1, party number 2, and party number n. So what we have is a situation where you have some input, S1, and this S1 can be any number from 0 to C minus 1, because these are going to be the way that we label these. So I'm just giving a picture, but so you have C possible measurement inputs, S1. Then there's going to be something that happens and you get an output, which we will label by M. So you get the same thing for the second one, and M2, so on and so forth. Sn, Mn. So this is the sort of picture. So just to formalize things a little bit, we have that we have a vector S of settings, which is just a tuple of numbers, S1 to Sn. C to the n. This just means that you have, so that means that for every Si that's in here, you have that they are an element of Z, this is not legible, Z sub C. Similarly, you have the outputs or outcomes. Those are the M's that I described before. So in a particular run of the experiment, you have a set of inputs, and then you have the outputs, which are going to be M1 to Mn. And each of these is going to be in, Mi could have D possible outcomes. So this one's going to be D, N, N. Okay. So when I do this experiment many times, I get a bunch of statistics. You know, I do input 0, 0, 0 all the way across. I get the outcomes, whatever they are. And when I do this many times, I get a bunch of statistics. And so the data that I get out of running this experiment is the following set of data. P of M given S, which more explicitly is something like saying that I do the inputs S1 to Sn, and I get outputs M1 equals X, X1, all the way to the output of Mn equals Xn, given all those inputs, which I'll write here, S1, S2, Sn. It could be the case that sometimes just a bit of notation maybe instead of writing all of this, I will just write maybe down here, P of M given S can be denoted when I need space as just P of subscript S and M, or more explicitly P subscript S M vector if I need something more. Okay. Any questions so far? So far, this should be similar to the setups that we've used already. So what is a correlator? So we're going to consider a particular function of the data, a linear function. Basically, we can interpret this, if you guys maybe think of the talk that I did last time, but for those that don't remember, there's this idea that you have the outputs of all the different sites. They get some M, I, and then there's some sort of local control computer that just does some linear process, just adds them together. So basically, I take these outputs, M1 to Mn, and then this local computer L just takes them and sums up the output. So this is the sort of operational procedure that I have in mind. So we're just going to be considering correlators, which I will write in the following sense. So P of K S, so following a similar notation to above, where this is PS, this K is sum I, Mi equals K. And how do you actually compute something like this? And I'll do an example. It's something like, this is saying that given a certain input, I want the probability that the sum of those inputs, whatever they may be, there's many different ways of getting this output K. So if this K is, say, 0, if this K is, say, 0, then, by the way, this arithmetic is all modulo D. So there's many ways to get this number K, and actually I'll just do an example. It'll be easier like that. So this more specifically is going to be a sum of the probabilities that I have up here. It's going to be something like a sum over all possible values of M, where I restrict this sum only to those where the sum of M equals to K of P, S, M. So let's actually just do an example to see how this works. Just the simplest example so we don't spend too much time on it. So if we have a bipartite scenario, we have something like, say that we just have one measurement setting, just the inputs are fairly easy. This is S1, this is S2, M1 equals 0, M1 equals 1. So this is also, I'm saying N equals D equals 2, and maybe C equals 1. That would just give me one box because Alice and Bob can only just choose from one measurement. You have one table of data. M2 equals 0, M2 equals 1. So you have some sort of thing like this, M, S1, S2. I'll just write it S vector again, 0, 0, PS 0, 1, PS 1, 0, PS 1, 1. So what is a correlator? So given that I have this data right here, how do I go to the correlators? Well, if I want something like P of M1 plus M2 equals 0, that's something of this form. Equals 0, how do I get this? I want all the probabilities here such that M1 plus M2 is equal to 0. I have two options. 0 plus 0 is 0, and in modular 2 arithmetic, I have 1 plus 1 equals 0. So this is P of 0, 0, S plus P of 1, 1, S. And you see that this is kind of exactly what's going on here. When the sum is equal to 0, I include it in the sum. If the sum's not in 0, for example, this one, it's not in the sum. Its weight is 0 here. Okay, so this is the idea of the correlator. So just as a side sort of remark, to sort of build off of the picture I drew before, am I going to be able to fit it here? Just quickly, in the CHSH scenario, maybe you guys will remember, I have a table of 16 numbers like this. Now, from each of these, the way that it's going to work out, from each of these little boxes, I'm just going to take the correlators, which is going to be like the diagonal elements or the anti-diagonal elements. So then I just have a set of 4 numbers, P equals something like this. It reduces the dimensionality of the problem. That means that you're not going to get everything, the full structure of the scenarios. No, if you just look at correlators, you're throwing away information, but it reduces the dimensionality of the problem. So maybe you can still say something interesting without having to work with all 16 probabilities. Or when you go to more higher N, higher D, and higher C, these things, the number of probabilities grow exponentially. So you want to just work with these correlators to reduce the dimensionality. Okay, so we also want to, so that was a little background on the no signaling part. So there's also this thing about computation. So we want to, so if we have this picture over here that we have in mind, we have a set of inputs, we have a set of outputs. We can think of this as a function. I don't know what Greek letter this was supposed to be. Z, C, N. I have a set of inputs, that's what I'm saying here. And I go to a set of outputs, Z, D, N. Okay, this is the first part where I'm taking each of these boxes. And then there's a part where you have this linear processor, which what it does is it takes these outputs and it sums them up. So what does that mean? That's just a map that says, okay, I'm going to take all of these numbers, add them up, so I just get a single number. And the arithmetic is modulo D. So basically, this whole process gives me a function that I'm interested. So what is a computation? It's a set of inputs to an output. I can think of this as being just composing these functions in some sense, such that I have this function f, which just brings me from Cn to Zd. And we'll be interested in, okay, what kinds of, so what's going into these boxes? Do you have some quantum entanglement? Do you have some other sort of correlations, local correlations, whatever? These will tell me the kinds of functions that I can compute actually. If I have just local hidden variables, there's certain kinds of functions I can compute. And if I have quantum or post-quantum sort of resources at hand, I can compute different not linear type functions. It will turn out that it's linear when you have local hidden variables. Question? Okay, good. Okay, so we need a definition here. So if you have this function c to the n to zd is called n-partite linear. And I'm going to use my own lingo for this. I'm just going to call this n-linear. In the paper, they keep saying n-partite, whatever. I think that's too long. Just n-linear is fine. If f of s equals j equals 1 to n, gj of sj. So what is this? G can be any sort of function that you want, but G is just a function from this input on a local site to this output on a local site. So this is n-partite linear. While G could be whatever it wants to be, it's linear on the parties. You're just summing up one function for each of the parties. Is this okay? Okay, good, because, so I'll just say this. This is sum of function from each site. Okay, good. Okay. So stochastic map, I will say something like this. Hopefully the notation is okay. So it's basically saying that I take a set of inputs and it gives me a probability, some number that's non-negative, something like this. So I have something like, oops. So if I have some set of inputs, it gets mapped to what? It gets mapped to P of S of, so this is the input, it's a function of this, K, which is greater than or equal to 0 for every one second. So how do you mean? So I'm taking, so I have a set of inputs and then I get a probability. I have one probability. Yeah. Yeah, I have ZD as an outcome. This is a probability distribution. Maybe I wrote this wrong. Let me see if I just went off script. So, okay, so what I can do is I know that f is a function from here to there, and I want this to just be a probability for each one. So maybe it will be just better to for every, so yeah, maybe this right-hand side is not right. It's not wrong, but it's a distribution over, okay, I will use Aziz's notation. It's a distribution over ZD. Is this right now? Yes. Yeah. Yeah, I honestly I just wrote it down now because I wanted to define something, but yeah. So there's a couple of things. Just Hoban does not deal with all of these probabilities, so we have this constraint that, of course, at least one outcome happens. So P S of K is 1, so this is normalized. So in order to not deal with this normalization, Hoban just gets rid of the 0th component. So, and just says that defines the 0th component to be 1 minus some k not equal to 0 of P S K. Just here, I have a distribution. There's k possible probabilities, but they have to sum to 1. So there's one that's dependent on the others. Just get rid of it. Do I have everything? Okay. Okay, so let's just look at the dimensional analysis. One second, analysis. Just to make it clear that this is, you're working with less probabilities. So I'll just do this using an example. So I will look at the CH-SH scenario, although it's not as stark here, actually. If you go to more complicated scenarios, the difference in dimension is much different. So you can compute that the dimension of the correlators, perhaps I should say this. Okay. one moment. I skipped ahead. My apologies. Let me go backwards for a second. Space of correlators. Let me. Okay, so we're gonna let. So P is going to be the space. It's going to be a convex space. It's going to be the convex space of correlators. And in fact, we have that if you just do some counting, you have that P is going to be embedded in some real vector space of some dimension. And this dimension is going to be equal to C to the n d minus 1. The d minus 1 is coming precisely because of normalization. So you have C to the n. This is the number of different measurement settings that you can have, right? You have C settings per party, so C to the n, and then times the number of probabilities per setting. So it's just, so C to the n, I will do the example now. Here you have C equals n equals 2. So you have 4 settings, and then you have 2 minus 1 correlators per each of these boxes. So it's going to be dimension 4, as we will see. Just a couple of facts about P. One, it's that, or just, yeah, so there are some inequalities, right? Which is just that P, S, K greater than or equal to 0. And 2, there are some also equalities like normalization or something, or other things. So we talked about in one of the talks, the beginning talks, that if you have a set of inequalities intersected by equalities, this is a polytope. So P is a polytope. Yeah, so now I just want to go to the dimension part of this, just to hammer home the point. So we have this example of CH, SH. And so here you have that n equals C equals D equals 2. In the CHSH scenario, you have, so the way that it usually works is that the dimension of the full no signaling polytope, dimension of NS, is the number of probabilities. There's 4 per square, minus the normalization constraints, there's 1 per square. And then it turns out that you want no signaling, which means that the marginals here and the marginals here agree. It turns out that there's 4 independent versions of that. So you have dimension 8. But if you look at the dimension of the correlator, this is, according to this formula, it's going to be 2 squared times 2 minus 1 equals 4. It turns out it's precisely actually the way that we've defined it. It's because we're setting the 0th, I set it over on the other board. You don't have to switch, Hoyu. Just we are setting the 0, we're not interested in the 0th, so k equals 0. So when you look at the k equals 1, that's when the sum of the numbers equal 1. So in this case, the correlators are just when you sum up these two. It's the anti-diagonal ones. Sorry, why? Why anti-diagonal? Yeah. So I will go back here for a second. We're setting the 0th one to be dependent. Yeah, we threw out the 0, not the 1. Yeah, exactly. Yeah, exactly. Yeah. By the way, yes, we can That's what I was also thinking. Yeah, we're always, so we're looking at these anti-diagonals. So we go from a space of 8 free independent parameters to 4. Okay, much more manageable.
How much we can know from this?
There's something that we can know about how much we can learn from going to this projection to upstairs. Yeah, there's some things that we can learn. Yes. Okay. By the way, so I will continue with this example, but I will sort of just. There's this sort of canonical example of these Popescu-Rohrlich boxes. I will just write them as PR boxes. So just to remember what it looks like, you have these 4 squares. I won't label everything, but it's just something like 1/2, 0, 0, 1/2, 1/2, 0, 1/2, 1/2, 0, 0, 1/2. So just to let you, what does the correlator look like for this? The correlator is going to be a vector of 4 numbers. What are those 4 numbers? It's these anti-diagonals that I mentioned before. So if I just label them like P of 0, 0, I only have 1 number per each box, so I will just write it like this. P of 0, 0, P of 0, 1, P of 1, 0, P of 1, 1. And in this case, I have that those are 0, 0, 0, and 1. Okay. So we have a local hidden variable, or HV variable, HVM, hidden variable model, if you have the following sort of thing happen. So you have that the no signaling distribution that you have is given by something like the right-hand side. Lambda is our hidden variable. P distribution over these lambdas. And product J equals 1 to N of P, and I will write this just more explicitly, Mj given Sj comma lambda. Why local? Because here these probabilities which tell you the response, the probability of getting an outcome given some settings and this hidden variable, it depends only on Sj. So that is only on the input at that local site. That's where the locality is coming in. So you just take a product over all of them. And then, in fact, this could be a deterministic sort of, this could be like a delta function. This is a theorem due to Fine. This could be a delta function, and you can absorb all the uncertainty of the outcomes into this distribution here, which is the uncertainty over the hidden variables. So this is the definition of a local hidden variables model. And of course, if you want to go to correlators, then you can do a similar sort of thing. So once you have a P, a no signaling distribution coming from a local hidden variable model, you can construct the correlators in the same way. So let's just talk about LB of correlators coming from HVM. So we have the following result, which is very nice. So consider an NCD Bell experiment. So just in the ways that I defined it before, then, L is the convex hull of n linear deterministic correlators. Okay, so the proof will be more pictorial, just to sort of get the idea across. So what we want is, we want all of the possible, so first let me just write this. Say that we have say that there's a correlator which is a vertex of this polytope. Okay, we're assuming that it's a polytope. By definition, it will be, so by definition, we want the following thing. We want this L to be the space defined by this. Say I have some correlators that look like this. Sum I mi equals f of s equals to 1. So this is some deterministic correlator. It equals, so it gives me precisely when sum of mi is equal to some function, it equals 1. Okay, and I'm defining L to be the convex hull of all possible, so I haven't defined what these f's are yet, so this is part of the theorem. They're going to turn out to be n linear functions, but let's just say that there's some f for right now. So the convex hull of such correlators. This is how you define this space L. And now we want to know what are these functions f that are coming from a local hidden variables model. So the picture is the following. So say that we have this array of measurement sites. And, sorry, where's my picture? Where'd my picture go? Okay, just making sure. Okay, so we are getting some inputs, S1, S2, Sn, and then imagine that if you have some local hidden variables model, you know that the function here that you can compute, given the input, I have just a local function g1, which gives me an output m1, and a local function g2, which gives me a function m2. This is what it means to be local model. So basically, just given the input, there's just a local function g1 that depends only on this input and not on the other inputs. So gn mn. So what you have here, maybe I should write it like this, is that this output is equal to g1 of S1, M2 equals G2 of S2, so on and so forth. So what does that mean? So when these outputs get given to this local control computer. What happens? You perform the following computation. Sum I mi is equal to sum I equals 1 to n. This is over all parties. I equals 1 to n of gi si. So what is this? This is what we called an n linear function. So that's basically the idea of the proof. Say that we have these that the vertices of this space are given precisely by deterministic correlators. So that's what do I mean by that? These correlators where these sum of mi equals some function. What functions are allowed? Precisely these functions. So that sort of just gives the basic idea of the proof. So if you have this Bell experiment, L is the convex hull of this n linear deterministic correlators. And precisely, yes, the n linear functions are the kinds of functions that you can compute in a hidden variable model.
How it look like when we have the
Oh yeah, by the way, yeah, so this is related to last week's talk. When you, okay, this is, I won't, yeah, we will talk about this later on as well, but what that means is that everything is, so I will just give a quick, when we have this n equals c equals d equals 2 case, each function is a map from z2 to z2, right? Yeah. So actually, there's something very pathological about this case. What that means that I can only just go from, say, some 0 to 0 or 1, or 1 goes to 0 or 1. Actually, each of these functions gi for each of the parties, Alice or Bob, actually gi is equal to the input. So it's some coefficient times the input plus some offset. They only look like this, because if I want to start from 0 and go to 0 or 1, I can always write this as either being a constant function or plus 1 or something like this. So the d equals 2 case is kind of pathological. So in that case, you just have sums of linear functions. That's what the n linear function looks like.
It's not telling me too much about the scenario.
Well, we know, okay, well, there's the following thing. Well, we do know that the PR boxes, yeah, it's not telling us anything that we don't know, but for the PR boxes, the function that we want to compute actually, for example, is, and maybe I'd be more explicit, this is for the PR box, and we will get to this, S1, S2 equals S1, S2. It's a nonlinear function. This will give you a PR box, right? Because what you want, again, I will go through this more detail later. You want a function such that the sum of the elements equals S1 times S2. This is going to be 0, so yeah, it's going to be equal to 0, 0. Okay, maybe this is not the best time to do it, but this will give you the PR box, but this is a nonlinear function. So there's something peculiar about the d equals 2 case that I will discuss in a second. Okay, so let's see. I had a couple of comments to make. I will just say them. One is that you see that there's a computational restriction on the kinds of functions that you're allowed to compute with the local hidden variable models. It's these n-linear functions. Yes, I think that that's the same sort of thing I want to talk about. So more generally, So let's consider more general correlations. What we want is the following. We want K, which is the sum of my outcomes, to be equal to some F of S, where F of S is not necessarily n linear. Not necessarily, it can be n linear. So there's a theorem that they want to prove, or that they want to say. So maybe I'll just write it down. Let's see, can I? Okay, yes. Okay, no, I guess I can't just write it because I use a different definition. So let me just include a couple of definitions so we can understand what's going on. So a bipartition bipartition B of n parties. Yeah, so say that we have many parties, Alice, Bob, Charlie, Doug, whatever. We want to partition them into two separate groups. So what do we want these groups to look like? We want subsets, A, B's, to be disjoint subsets of 1 to n, disjoint. This is one thing, and then we of course want the union of them to be all the possible parties, 1 to n. Okay. Okay, and then so in order to state the theorem, they use a special kind of function. So let me just write down what this is. So this is this function Cn to Zd is called I know that there's a technical sense in which the word bilinear is used, but so I don't think that this is, I'm not using it in that sense, I don't think. I'm just, because it's nicer than saying what they used all the time. So we call it bilinear if f of s is equal to fa of sa plus fb of fb, where we have the following properties. So for some I, which is a or b, you have that each of these functions, fa or fb, goes from the number of parties to zd. And also you want that SA, the way that I have it here, so these are vectors as well, SI is equal to take the set of inputs and just look at only those that are concerning that those set of parties. So I think it's kind of clear to see how that notation works. So they have this special sort of function bilinear. And then we can say, I called it bilinear. I know that bilinear has a different technical meaning. Yeah, exactly. Yeah, I don't think that it's bilinear. No. Can I think of it like this? I actually think it might be. I actually think it's okay. Yeah. Instead, they were saying something like it's, what were they calling it? Like n-partite something. They gave it a long name, and I just said, okay, bilinear. I think it works. Okay, so here's what it is. For every f of s compatible with okay, 1 second, sorry, for every s and we have the corresponding correlator. You tell me, Hoyu, if you can see this. F of s, and I will just write it like this. For every function like this and the corresponding correlator, or P of x, is compatible with okay. Let's give it a special name. So just to let you know where I'm headed, the following is what we're looking at. Say that we have a correlator that deterministically computes some function. In what case can we say something about the no signaling distribution that it comes from? So that's what we want to say, that there's the following statement. The correlator uniquely specifies a no signaling distribution if and only if the function here is not bilinear. So that's kind of where we're going from. We want to go from this space of correlators. In what case can we infer something about this the distribution that it comes from that's compatible with it? Okay, so here's the no signaling distribution. It's d to the 1 minus n if k equals f of s and 0 otherwise. And then there's more to the statement. If f of s is not bilinear, then p bar s of m is the only such is unique no signaling distribution. It so happens to be the case that when we deal with the CHSH scenario, these so this says that it's a unique no signaling distribution. It doesn't say that it's a vertex. There's another result which says that this will then also be a vertex. But so in the CHSH scenario, we know that actually it turns out that the PR boxes are completely determined by their correlators. So we will look at that example in a second. Or should I? No, okay. I will just sketch this proof very quickly. There's a couple of things that you want to check. First is compatible. Compatibility. I actually always spell this wrong. Compatibility. I don't know. I think this is okay. So what do I mean by compatibility? I don't want to go over there and make Hoyu work too much. What's that? Yes. Yeah, D still prime. What do I mean by compatible? In the following sense, that if I compute the correlate, so I gave you the no signaling distribution. if I compute the correlator from this using the expression that I wrote down originally, where you marginalize essentially, then you recover this you go from the no signaling to the correlator. So that's what I mean by compatibility. You can check that this works. So the second part of the proof that they're interested is that if f of s is bilinear, so if f is bilinear, they come up with a counterexample showing that it's not unique. And I will just write this here, maybe with a tilde. You have d to the 2 minus n, such that if I sum over I element of A, mi equals fa sa. Sorry, this is not easy to read. fa sa and sum I element of B. You have this entry if you satisfy these two constraints, and then 0 else. The point just being that if you come up with a counterexample, it means that if it's bilinear, there's at least another one, so that distribution is not unique. And then there's a third thing that they have to show, which is that there's this lemma, which is something along the following lines. If you have some f, which is a bipartite sort of thing, just I have two parties, each taking from C measurements to ZD, which is not bilinear, then the only distribution compatible with PS of k equals f of s is if there's just two parties, m1, m2 equals d inverse m1 plus m2 equals fs, 0 else. Okay, so I'm not going to go through the whole thing. It's fairly long, but basically you show that they're compatible. Okay, that works. You show that if it's bilinear, it's not unique. And then there's this additional step that say that you have just two parties, then the only distribution compatible in this bipartite scenario is precisely this one. Then what you do is you do some sort of induction. You look at all the possible different bipartitionings of your n parties, and you consistently use this this distribution here. You get that that's the only compatible no signaling distribution with our correlator. Okay, so now we want to show that actually that distribution is a vertex. So we will first prove this proposition, which is that every P element. So every no signaling distribution corresponding to a vertex of P. Remember, we have a distribution in no signaling, and then say every time you have a no signaling distribution, so just remember, what am I thinking of? SM, and then the correlator is something like SK equals the sum of those, right? So every distribution which corresponds, that is when I sum over the proper probabilities, that I get these correlators. So every no signaling distribution corresponding to a vertex of P. So I said before that, maybe I didn't say this, I will write it. The vertices of P, which is the set, I defined P, right? One second. Yeah, I did define P. So it's a polytope, I mentioned that. So if you have a no signaling distribution that corresponds to a vertex of P, that is some correlator, then, okay, corresponding to a vertex of B lies in a facet of no signaling, lies on a facet of no signaling. Okay, I will leave this question mark here. They say facet, and I want to say that there's nothing that they say. So what is a facet? Facet is the is a face of a polytope that's one dimension less. So if you have a cube that's 3 dimensions, each of these.
Like this here. It's not like this.
Here?
Yeah.
Which one are you saying? You think it's facet?
No.
Yeah. No, they say facet, but I think what they mean is just face. It's some extremal. It's some extremal part of the polytope.
It's obvious that it's subconvex because you do it with the vertex. So if you
Yeah.
convex, it's convex.
Yes.
So what you say, if it's unique, then it's a vertex indeed, right?
Yeah. So every corresponds to a vertex of P lies on a facet. Yes, it lies on a facet. But then when you combine that with this theorem over here, or there somewhere, then you will have that. If you have a specific kind of correlator which computes a non-bilinear function, then it comes to a unique vertex upstairs.
We have something more here because
Yeah.
Everything, every vertex in this facet will be vertex in the whole polygon.
Yes.
It's something not about like Nancy, like it's something general.
Yeah. Yes. Exactly. Yeah. So there's some things that I think we can improve on. So the proof, I'm not going to go through it, but here's the basic idea of it, which is the following. Say you have some region of the non-signaling distributions, and these are, so I will, so this is my correlator. So if it's compatible with some, so if I have a distribution which is compatible with a vertex, what it means is that when I do this summation, I always come to this, and so there could be many of them. So this is my polytope P, this is NS. So say I look at the vertices which project down to my correlator, which is a vertex, then the convex sum of them will be some convex subregion of, like you said, it will be some sort of convex subregion of this no signaling polytope. And then, so what would it mean for this to be actually a facet of the polytope, it means that there's no two other points. One second. Let me use a different color. Say I have two other vertices here and here. That means if this was to be a facet, it means that there cannot be any convex line that goes between the two. So the question is, let's call this region, this square region that I have here, F. Is this a face or not? Well, if it was not a face, then let me think. Yeah. So if it is a face, then there does not exist two other vertices such that their convex combination intersects this F. However, these two blue dots are not compatible with my vertex. So this one will project, say, to some point here. This one will project to some other point here. So the sort of idea is that this must be a face because because I've already included all of the vertices which project to here. If there were some other vertices which intersect it, then I could take a convex combination of them and I could land inside of this face, and then it would project down here. But by assumption, I already have all of the vertices that are projecting there. So it means that once I have taken these into account, there can be no such convex line. So, and if there's no possible convex, I agree. I'm not sure that this is a facet, by the way. I have.
Because you can take the box and you can take vertex in the cube.
Yeah.
Like even vertex.
Yeah.
And you have just the line.
Yeah.
No, it's not a facet, but it's convex set by itself.
Yes. Yeah, I think that more thinking needs to be done here. They were not very precise with it. But yeah, their claim is that this is precisely a facet.
But everything that I don't know if they mention it, every vertex in this, they call it facet. Okay, let's call it facet.
They're calling this facet this region here. Okay.
The vertex in this facet is the vertex in the whole polygon. Like this is the thing.
Yes, these are vertices of the whole of NS. These four dots, right? Okay, these are vertices of NS. And so what is the convex subregion that's spanned by these? This is F. Okay, now F is a face. When is F a face? If there's no other intersection with this F. Actually, now I'm thinking about it again. I'm reminding myself, I think that it's okay. Because by definition, for something to not be a face, it means that there is such a set of vertices such that their convex intersects here. But there is no such convex that intersects here. Yeah.
But it's not like a facet have to be like in dimension more, like.
That's why I said face. I'm not. Yeah, it could be a face, but it could be some extremal. It could be some extremal subpolytope.
If you have a cube, you can consider the line as in a cube.
Yeah.
The line as a facet. This is a quotient. So if it's not.
Yeah. No. I agree. I'm not sure that it's a facet because to say it's a facet, you have to say something about how many vertices there are here. By the way, there's got to be a certain number. They did not show this at the very least. I think it could be I think it's a face is what they show. They don't show that it's a facet to my understanding. But anyway, face actually suffices, I think.
What is the definition?
Facet has definition. It's in a polytope of dimension D, you need at least a facet needs to be incident on at least D vertices, affinely independent. It's not obvious to me that this is the case here. Anyway, okay. So then once you show that this every no signaling distribution that corresponds to a vertex of P lies on a facet of NS, you combine that with this result over here that you have that also that there's a unique no signaling distribution when you have a certain function being computed. So if it also lies on a face and it's unique, it means it's a vertex. So that's just me saying it, which is P bar S M is a vertex of NS if and only if Fs is not bilinear. Okay. So, okay. I will not. Okay, so there's still a couple more things that I want to talk about just briefly. Bell. Whoa. I butchered this spelling somehow. So here is what we want to look at. Say we have this picture, something like this. And I will first draw and maybe I will use another color if I have it, just for this quantum region. Maybe. Okay, so here's the thing. We have so Bell inequalities are useful because what they do is they separate, say this is my quantum region. Put this here. This is my set of general correlators. Always we're working with correlators, by the way. And then this is this space L. So what's nice about Bell inequalities that are tight are facet Bell inequalities. Those are ones that lie precisely on the facet of this polytope. And so this is called a facet Bell inequality. And so these specifically divide the local and the non-local regions. So, but they're very difficult to find these facet Bell inequalities. So sometimes what people might do is just come up with other Bell inequalities. So there's a couple of different types that they define here. And I think that they're okay. So trivial, what is that saying? Something like PSK greater than 0. Trivial, it's just if it's greater than 0, that's something simple. You have also these facet Bell inequalities. What are these? These are necessary and sufficient for a distribution to be classical for a local hidden variables model. These specifically, but then you can think of a third type which they call non-trivial. Geometrically, what are the non-trivial ones? Geometrically, the non-trivial ones are something like this. Maybe it's not easy to see there. Maybe I'll go over here. The thing about the non-trivial ones is the following, that it's necessary. So if you want something to be local, they're necessary, but not sufficient. for local hidden variable model. But that's okay, because sometimes it's okay to just have necessary conditions, because you could still have quantum violation of it, and that's okay. So just something that we know, for instance, that anything that's local hidden variable has to be inside of this inequality, but we know that maybe it's not that tight, maybe it's not right on this edge. But it's okay, because maybe still there's a quantum violation, and that's still useful. So how do you define these non-trivial ones? Okay, so actually, the thing that's nice about the CHSH scenario is that we will see that the facet Bell inequality is the same thing as, so the way I define non-trivial is that it's necessary but not sufficient, but sometimes they can be. Non-trivial is the way that you define the inequality. It's not necessarily whether it is necessary and sufficient, but this is like a heuristic, like a rule of thumb. So actually, maybe I just write down when this is a non-trivial Bell inequality. Let me actually just write it down, and then I'll give an example. So what does this non-trivial Bell inequality look like? So in general, just a general Bell inequality will first look something like this. You have some sum over the inputs and the outputs with some coefficients, Ks, times the correlator is less than or equal to some gamma L. Okay, this is the general thing that you're looking for. If you want to define a non-trivial Bell inequality, then they will have this following form. So you sum over the inputs of some input distribution. Imagine that you are getting some inputs at some random frequencies. K delta K f of s. So again, what am I saying here? I only want those, I want to only sum up those terms where the sum of where this is, remember, is sum of my m's equal to some function. And this has to be less than or equal to, I will write this down here instead, less than or equal to the supremum over g of s, p of s, delta f of s, g of s, where, so I will say it over here, g of s is n linear. Okay, so let me unpack this just a little bit. So what's going on here? Did I have this all the way? No, there's a correlator here. Okay, so now it's correct. Say I have some distribution of inputs. It could be random. It could be 1 over the number of inputs. And what is going on here? I want to sum over only those correlators. I want to sum up all my correlators that equal this function, and this is less than or equal to this thing. I'm going to give an example because I think it will make this make more sense. But essentially what you're doing is to say, let me look at all possible n linear functions, and what is the maximum possible value that I can get for this? That is to say, when does this function, which is not n-linear, and this one that is n-linear, how many places do they match up? And that gives me roughly the maximum that I can have. Let's do an example. So again, the canonical example is CHSH, but we can do it for other ones as well. So the CHSH inequality can be, we saw this last time, can be written like this. Over S, sorry, not like this. Delta K S1 S2 P S K less than or equal to 3/4. Okay, this is the CHSH inequalities written in a different way. How do you see this? You only want, so what does this look like? It looks something like, so this looks something like P of, let's see, it's only when this K equals this product. So when you have 0, 0, you need K to be equal to 0 plus P of 0, 1. So when does this S1, S2, what does this equal? 0 times 1 is 0. 0 plus P of 1, 0, 0 plus P of 1, 1, 1 less than or equal to 3/4. In the last seminar, I showed that this expression actually is the same as the one that we're used to, so I will not do it again. It was with some different flipping of the zeros and ones, but it's the same. So how does this look like the one that we have over here? So consider, how do we find that right-hand side? The right-hand side is found by varying over all possible n-linear. So, for example, an example of this for CHSH is the constant function. This is linear, right? Say that it equals 0. Then for G00, you have that this equals 0. G11 also equals 0. What about my function f? In this case, f is f of S1, S2 equals S1, S2. So what is it here? F of 0, 0 equals 0. It's just these. It will be 0, 0, 0, and then f of 1, 1 equals 1. So the 3 is coming from, so I want to take the maximum over all possible places where I take some function that's bilinear or n-linear in the general case, and then see how many times it matches up with my function on the right-hand side. It matches up 3 times, so that's where I get the 3 from. The 1/4 is coming from the fact that I chose, in the general case, this is my P of S. We can take it to just be a uniform, 1 over the number of inputs. So so you can do this, in general, you can just define these inequalities like this. You define them in the following sense. Say that I have some nonlinear function and say, okay, what is the best I can do by computing these, this function using n-linear, where here it could be something like 0. And that gives you a kind of Bell inequality that's in general necessary but not sufficient for locality. Okay, so I think that I'm almost wrapped up. I just want to say one last thing. I didn't get to the part about MBQC more specifically, but there's something that's worth saying. So with MBQC, there is a wrinkle. So let me see. There's one major difference, which is the following. say I have some set of inputs, S1 to Sn, and then I have this linear control computer. What it can do is it can do some sort of linear operation, say Q times S. And this linear operation will in general make it so that the input that, so I will say H equals QS, so that the input that ends up going into, say that this is H1, right? This is some linear operation. In principle, it could mix up all my S's in this step. So I could have this pre-processing go such that I go from here, it does some stuff to it, and then H1, and then I compute some, and then I get some output from this, M1. And I do this for all of them. This pre-processing step where HI is equal to some Q, let's see if I get this right, J, IJ, SJ, something like this. When I do this sort of procedure, what ends up happening is that even if I have a local hidden variables model, I can compute nonlinear functions. Not all of them, but I will be able to compute some of them. And it's precisely, and they're not n-linear. They're, I will have cross terms between this S and this one in general, in the general case. And that means that I can compute some non-n-linear functions when I do MBQC. This is the key step of MBQC. You have this linear control computer, takes the inputs, performs some sort of linear operation, and then when I get an output, even if it's local hidden variable model, I will get something that's not n-linear in general. But there's a maximum degree to which this can be computed, and it depends on the number of outcomes D, which I didn't have time to get into. But actually, luckily, Hoyu, the next talk that we will do, which will resume in like a month, he will actually go into much more detail about actually how this MBQC changes depending on the number of outcomes. This pre-processing step, mixing all the inputs together, will in general make you be able to compute more richer space of functions. Okay, so that's all that I have to say for this. I will see you guys in a month or so. Yeah.